On the 1st of July, 2025, a robotic telescope in Chile captured something extraordinary. The Asteroid Terrestrial Impact Last Alert System, known simply as ATLAS, scans the night sky every clear evening, searching for asteroids that might threaten Earth. This particular network operates 2 telescopes in Hawaii and 2 in Chile, methodically photographing the same patches of sky night after night. By comparing these images, astronomers can spot anything that moves against the background of distant stars. What the ATLAS team discovered that night appeared at first as an unremarkable dot of light, faint, barely visible even to their sensitive instruments. But dots that move are never truly unremarkable to asteroid hunters. Every moving object gets flagged for follow-up observations and orbit calculations. Within hours, astronomers around the world turned their telescopes toward this newcomer, gathering the precise measurements needed to determine where it came from and where it was going. The calculations came back unusual, very unusual. This object was not orbiting the Sun in the typical manner of asteroids or comets. Its path through space followed what mathematicians call a hyperbolic trajectory, which means something profound. It arrived from interstellar space, the vast darkness between star systems. It would pass through our solar system once, never to return. Gravity could not capture it. This visitor belonged to the galaxy itself. Humanity had detected its 3rd confirmed interstellar object. The designation came quickly, 3I/Atlas, following the naming convention established for interstellar visitors. The I stands for interstellar. The number 3 indicates our 3rd confirmed detection. ATLAS honors the survey that found it. To understand how rare this achievement is, consider that humans have been systematically searching the skies with modern telescopes for over a century. We have catalogued hundreds of thousands of asteroids. We have tracked comets by the thousands. Yet, in all that time, all those observations, all those countless nights of watching, we have confirmed exactly 3 objects that originated beyond our solar system. The first arrived in October 2017. Astronomers named it I/Oumuamua, a Hawaiian word meaning scout or messenger. That object puzzled scientists immediately. It showed no tail, no fuzzy cloud of gas and dust that typically surrounds active comets. Its shape appeared extremely elongated, perhaps 10 times longer than wide. Most mysteriously, it accelerated slightly in ways that could not be fully explained by normal physics. Some researchers, most notably Harvard astronomer Avi Loeb, suggested it might be artificial, perhaps a light sail from another civilization. The debate continues. The second visitor came in August 2019. Astronomers called it 2I/Borisov after its discoverer, amateur astronomer Gennady Borisov. This one looked reassuringly normal. It had a prominent tail. Its chemical signature matched typical comets perfectly, showing water vapor and carbon monoxide. Borisov proved that interstellar visitors could be ordinary travelers, just comets that happened to form around other stars. Now 3I Atlas joined this exclusive list. Early observations suggested it was active, developing a faint coma, that fuzzy cloud of gas and dust that forms when ice sublimates in the warmth of approaching sunlight. This meant scientists could study its chemistry directly by analyzing the light passing through its atmosphere. The composition of that gas would tell stories about where this object formed, what materials were present in its birth system, and what conditions it experienced during its long journey through space. The discovery timing proved fortunate beyond measure. Previous interstellar visitors were detected late, often after their closest approach to the Sun, when they were already racing back toward the darkness. 3I Atlas was found early, months before its most important encounters. This meant humanity had time to prepare, time to coordinate observations, time to aim our greatest instruments at this messenger from beyond. Asteroid hunters had stumbled upon something profound. Somewhere out there, orbiting a star we may never identify, a planetary system had ejected this wanderer into the cosmic void. It drifted for perhaps millions of years through near-perfect vacuum, surviving temperatures barely above absolute zero, bombarded constantly by radiation. Now it had entered our neighborhood, offering humanity an unprecedented opportunity to examine materials forged in alien environments. The wanderer had arrived. The questions were just beginning. Understanding what makes an object truly interstellar requires grasping a fundamental concept in orbital mechanics called eccentricity. This single number describes the shape of any orbit, and it carries profound implications for where an object came from and where it will go. Imagine a perfect circle. In mathematics, a perfect circle has an eccentricity of exactly 0. Every point on that circle sits at precisely the same distance from the center. Now, imagine stretching that circle into an oval, an ellipse. As the oval becomes more elongated, more stretched, the eccentricity value increases. Earth orbits the Sun in a nearly perfect circle with an eccentricity of just 0.017. Our planet's distance from the Sun varies by only about 3% throughout the year. Comets that belong to our solar system travel on much more elongated paths. Halley's comet, which swings past Earth every 76 years, follows a stretched ellipse with an eccentricity of 0.967. When Halley's approaches the inner solar system, it gets close enough to warm up and develop its famous tail. Then it races back out beyond Neptune's orbit, spending most of its time in the cold darkness of the outer solar system. But crucially, Halley's always comes back. Its orbit, no matter how stretched, remains closed. The Sun's gravity holds it captive. Here lies the mathematical boundary that separates local from interstellar. Any orbit bound to the Sun, any closed path that will repeat eternally, must have an eccentricity less than 1. Objects with eccentricity, values between 0 and 1 trace, ellipses of various shapes. They belong to the solar system permanently. But if an object has an eccentricity equal to or greater than 1, everything changes. An eccentricity of exactly 1 produces a parabola, an open curve that extends to infinity. An eccentricity greater than 1 creates a hyperbola, another open curve with distinct mathematical properties. Objects following these paths are not bound to the Sun. They arrive from interstellar space, swing past our star once, and depart forever into the galactic void. 3I Atlas has an eccentricity greater than 1. This is not interpretation or theory or speculation. This is measured geometric fact derived from precise observations of the object's position over time. Astronomers tracked its movement against the background stars, measured its distance, calculated its velocity, and determined its trajectory with the same mathematical certainty that predicts planetary positions decades in advance. The object entered our solar system from the direction of the constellation Ursa Major, the Great Bear. It arrived carrying velocity that originated not from our Sun's gravitational influence, but from the complex gravitational landscape of our galaxy itself. Perhaps it was ejected from another planetary system during that system's chaotic formation period. Perhaps gravitational interactions with giant planets flung it into interstellar space. Perhaps close encounters with neighboring stars during a cluster's dispersal sent it wandering. Whatever mechanism launched 3I Atlas on its journey, the object traveled through the darkness between stars for an unknowable span of time. Interstellar distances are so vast that even traveling at tens of kilometers per second, the journey from another star system to ours likely consumed millions of years. During that entire voyage, the object drifted through near-perfect vacuum. The density of matter in interstellar space is so low that a single cubic centimeter might contain only one atom. For comparison, a cubic centimeter of air at sea level on Earth contains roughly 25 billion molecules. Throughout its journey, 3I Atlas endured continuous bombardment by cosmic rays, high-energy particles that stream through the galaxy. This radiation slowly altered the object's surface chemistry, breaking apart molecules, creating new compounds, perhaps darkening its exterior. By the time it reached us, 3I Atlas carried chemical fingerprints reflecting both its original formation environment and its long exposure to the interstellar medium. The mathematics tell us with absolute certainty that this visitor does not belong to our solar system. It came from elsewhere, from environments we can only study indirectly through these rare messengers. After it completes its pass through our neighborhood, 3I Atlas will depart back into the darkness, continuing a journey that may last until the end of time itself. The sun's gravity will bend its path but cannot hold it. The wanderer remains forever free, forever traveling, forever carrying within it secrets of alien stellar systems we may never directly observe. When astronomers finished calculating the trajectory of 3I Atlas, they discovered something remarkable. The object's path through our solar system would carry it past multiple planets at distances close enough for detailed observation. This cosmic choreography offered humanity an unprecedented opportunity to study an interstellar visitor throughout different phases of its journey. The timeline read almost like a carefully planned tour. First stop, Mars, on October 3rd, 2025, when 3I Atlas would pass within approximately 30 million kilometers of the red planet. For context, that distance equals about 1/5 of the gap between Earth and the Sun. Close enough that spacecraft orbiting Mars could potentially observe the visitor with far greater detail than Earth-based telescopes could manage. Next came the most critical milestone, perihelion, the point of closest approach to the Sun. This would occur on October the 29th, 2025, when 3I Atlas reached a distance of 1.36 astronomical units from our star. 1 astronomical unit equals the average distance between Earth and the Sun, roughly 150 million kilometers. At perihelion, solar heating would reach maximum intensity. Ice would sublimate most vigorously. Any volatile materials hidden within the object's interior might reveal themselves through outgassing patterns visible to our instruments. But perihelion presented a significant observational challenge. The geometry placed 3I Atlas behind the Sun from Earth's perspective. For several weeks surrounding closest approach, the glare of our star would make direct observation from Earth impossible. It would be like trying to spot a candle flame positioned directly behind a searchlight. space-based observatories stationed at different positions in the solar system might maintain sight lines, but Earth's view would be blocked during the most active phase of the visitor's passage. Then, on December 19th, 2025, 3I Atlas would emerge from behind the Sun at a distance of approximately 1.8 astronomical units from Earth. This represented optimal viewing conditions, close enough for detailed study, yet far enough to avoid solar interference. The world's most powerful telescopes, both on the ground and in space, could coordinate comprehensive observations. Spectroscopy would reveal chemical composition. Imaging would capture morphology and activity patterns. Photometry would measure brightness variations that might indicate rotation or changes in outgassing intensity. The grand finale would arrive on March 16th, 2026, when 3I on Atlas would approach within 0.36 astronomical units of Jupiter, roughly 54 million kilometers. This represented an exceptionally close encounter with the solar system's largest planet. Jupiter's powerful gravitational field would bend the visitor's trajectory, the final major perturbation before 3I Atlas departed back into interstellar space. Any spacecraft operating in the Jovian system might capture observations impossible from Earth's distance. This sequence of encounters spanning 9 months offered something astronomers had never possessed before with interstellar visitors. 1I Oumuamua was discovered after perihelion, already racing away from the Sun when we first spotted it. 2I Borisov received more advance warning, but still provided only a few months of observation time. 3I Atlas offered the most generous timeline yet. Early discovery combined with a trajectory that visited multiple observation posts throughout our solar system. Some noted that this fortunate timing seemed almost too convenient. The object approached Mars when that planet hosted multiple active orbiters equipped with cameras and spectrographs. It passed Earth at a distance neither too close for safety nor too far for detailed study. It visited Jupiter when several missions either operated there or traveled through that region of space. The coincidences accumulated in ways that made a few researchers uncomfortable, though most recognized this as simple good fortune, probability working in humanity's favor for once. The spacing of these encounters also meant that scientists could track how 3I Atlas evolved as solar heating increased, then decreased. Observations at Mars would establish baseline properties, while the object remained relatively inactive. Perihelion data would capture maximum activity. Post-perihelion observations from Earth would document how the visitor responded after experiencing intense solar radiation. The Jupiter encounter would provide a final snapshot before 3I Atlas escaped into the outer solar system and beyond. Mission planners at space agencies worldwide began coordinating observation campaigns. European assets at Mars, American telescopes on Earth and in orbit, Japanese instruments, contributions from observatories across every continent. The cosmic clockwork had aligned perfectly. Now, humanity needed to capitalize on this rare opportunity before the wanderer departed forever. Within days of the discovery, telescopes around the world began gathering light from 3I Atlas. Every photon captured told part of the story about this visitor from beyond. The early observations focused on basic characterization, measuring brightness, tracking position, searching for signs of activity that would indicate whether this object resembled a comet or an asteroid. the Swift Observatory, a space telescope designed primarily to detect gamma-ray bursts from distant cosmic explosions, turned its ultraviolet and optical instruments toward the newcomer. Swift carries sensors particularly sensitive to specific wavelengths of light associated with certain molecules. When astronomers examined Swift's data, they found something unexpected. The telescope had detected hydroxyl emissions. Hydroxyl consists of one oxygen atom bonded to one hydrogen atom, written chemically as OH. This molecule does not exist naturally in isolation for long because it reacts quickly with other substances. When astronomers detect hydroxyl around comets, it serves as a signature for water vapor. Sunlight breaks apart water molecules, a process called photodissociation, creating hydroxyl that briefly exists before reacting with other materials or drifting away into space. Finding hydroxyl around 3, Atlas confirmed that the object contained water ice and was actively sublimating, transforming directly from solid to gas without passing through liquid phase. This made it a comet rather than an asteroid. But the distance at which Swift detected this activity raised immediate questions. 3. I Atlas was approximately 3.5 astronomical units from the Sun when hydroxyl appeared. For context, Mars orbits at about 1.5 astronomical units. Jupiter sits near 5 astronomical units. The visitor was still quite distant, well beyond Mars's orbit, in a region where solar heating remains relatively weak. Most comets from our solar system do not begin significant activity until they approach roughly 3 astronomical units from the Sun. Some remain dormant until they get even closer, within 2 astronomical units. The threshold depends on composition, particularly which volatile materials dominate the ice mixture. Water ice requires more heating to sublimate compared to more volatile substances like carbon monoxide or carbon dioxide. Yet 3I Atlas had begun venting water vapor far earlier than typical solar system comets. Either its surface was extraordinarily porous, allowing solar radiation to penetrate deep enough to warm subsurface ice, or its composition included volatile materials more reactive to faint sunlight than pure water ice, or something about its structure made it more responsive to solar heating than expected. This early activity suggested the object's interior might be unusually rich in volatiles, containing substantial reserves of frozen gases that could sublimate readily. Alternatively, the surface might be darker than typical comets, absorbing solar radiation more efficiently and converting that energy into heat more effectively than ice-covered surfaces that reflect much of the incoming sunlight back into space. Scientists began modeling different scenarios. Perhaps 3I Atlas formed in an extremely cold environment, so distant from its parent star that even highly volatile materials froze into the ice matrix. Perhaps its journey through interstellar space somehow altered surface properties, creating a structure that responds to heating differently than comets that formed and evolved entirely within our solar system's protective environment. The hydroxyl detection also meant astronomers could begin tracking how gas production rates changed as the object approached the Sun. By monitoring the brightness and extent of hydroxyl emissions over time, they could map how sublimation responded to increasing solar flux. This would provide crucial insights into internal structure and composition. Ground-based observatories joined the campaign, their larger mirrors gathering more light and enabling higher resolution spectroscopy. They began searching for other molecules that might be present in the coma, the fuzzy cloud of gas and dust surrounding the nucleus. Each detected molecule would add pieces to the puzzle of where this object formed and what materials were available in its birth environment. The early activity also meant that by the time 3I Atlas reached perihelion, it would likely be very active indeed. Solar heating increases with inverse square of distance. At perihelion, radiation intensity would be roughly 6 times stronger than at the current distance. If the object was already venting water vapor now, the peak activity could be spectacular. Questions multiplied faster than answers. Why was this comet active so early? What unusual properties distinguished it from solar system comets? The hydroxyl detection transformed 3I Atlas from a simple interstellar visitor into an active comet with behavior that defied conventional expectations. The James Webb Space Telescope represents humanity's most powerful tool for analyzing the chemical composition of distant objects. Positioned far beyond Earth's atmosphere at a gravitational balance point called L2, Webb carries instruments sensitive to infrared wavelengths that can detect molecules invisible to optical telescopes. When astronomers pointed Webb's near-infrared spectrograph toward 3I Atlas, they expected to find the usual comet chemistry dominated by water vapor. What they found instead rewrote expectations entirely. The data revealed a carbon dioxide to water ratio of approximately 8:1. For every molecule of water vapor escaping from 3I Atlas, roughly 8 molecules of carbon dioxide accompanied it. This ratio stood in stark contrast to typical solar system comets, where water dominates overwhelmingly. In most comets we have studied, water vapor outweighs carbon dioxide by factors of 10 or more. 3I Atlas showed exactly the opposite pattern. This chemical signature carried profound implications. The ratio between different volatile materials in a comet reflects the temperature and composition of the environment where that comet formed. Water ice condenses from gas at warmer temperatures compared to carbon dioxide. In the standard model of solar system formation, water ice begins condensing when temperatures drop below roughly 170 Kelvin, about -100 Celsius. Carbon dioxide requires even colder conditions to freeze, typically below 65 Kelvin, roughly -200 Celsius. The regions of our solar system where most comets formed, the areas beyond Neptune's orbit where temperatures were cold enough for ice to accumulate, still maintained conditions where water ice formed more readily than carbon dioxide ice. The resulting comets naturally contained more water than carbon dioxide, reflecting the temperature gradients and available materials in the young solar system's outer reaches. But 3I Atlas told a different story. Its chemistry suggested formation in an environment far colder than the regions where our comets originated. Perhaps it condensed in the outermost reaches of another stellar system, in zones so distant and cold that carbon dioxide froze more efficiently than water. Or perhaps it formed around a star with different properties than our Sun, creating temperature distributions that favored carbon dioxide retention over water ice. Some researchers proposed alternative explanations. Perhaps 3I Atlas had experienced thermal processing during its interstellar journey. Encounters with other stars, even distant ones, could have warmed the object enough to preferentially remove water while leaving the less volatile carbon dioxide behind. Cosmic ray bombardment over millions of years might have altered surface chemistry in ways that changed how different volatiles sublimated once the object entered our solar system. Another possibility involved the object's internal structure. If 3I Atlas had a layered composition with carbon dioxide-rich materials near the surface and water ice deeper inside, the current activity might reflect sublimation of outer layers. As the object approached closer to the Sun and heating penetrated deeper, the ratio might shift toward more water-dominated emissions. The chemical fingerprint also raised questions about the diversity of planetary systems throughout the galaxy. If 3I Atlas represented typical chemistry from its birth system, then that system operated under very different conditions than our own. The materials available, the temperatures during formation, the processes that shaped planetary development must have differed substantially from the environment that produced Earth and its sibling worlds. Astronomers began searching for additional molecules in the spectra. Webb's instruments could potentially detect carbon monoxide, methane, ammonia, and various organic compounds if they existed in sufficient quantities. Each new detection would add detail to the chemical portrait, helping narrow down the possible formation environments that could produce such unusual composition. The carbon dioxide dominance also meant that 3I Atlas might remain active across a wider range of distances from the Sun compared to water-dominated comets. Carbon dioxide sublimates more readily than water ice, requiring less solar heating to transition from solid to gas. This could explain the early hydroxyl activity detected when the object was still beyond Mars's orbit. If substantial carbon dioxide was already venting, it could drag along water vapor through physical processes, creating the observed hydroxyl emissions. The chemical fingerprint distinguished 3I Atlas not just as an interstellar visitor, but as a messenger from environments profoundly different from our cosmic neighborhood. Its composition spoke of alien stellar systems, where planets formed under conditions that remain largely theoretical to astronomers studying only our own solar system's architecture. When the Hubble Space Telescope captured high-resolution images of 3I Atlas, astronomers noticed something peculiar about how light scattered from the object. Most comets display a predictable pattern. As they approach the Sun, solar radiation heats the nucleus, causing ice to sublimate. The resulting gas carries dust particles away from the surface, creating a cloud called the coma that surrounds the solid nucleus. Solar radiation pressure then pushes this dust away from the Sun, forming the characteristic tail that always points in the anti-solar direction, away from our star. 3I Atlas showed this expected tail extending away from the Sun, a faint streak of dust and gas being swept backward by solar wind and radiation pressure. But it also displayed something unusual, a brightness enhancement on the side facing toward the Sun. This forward glow appeared as a fan-shaped brightness extending from the nucleus in the sunward direction, exactly opposite to where comet tails normally appear. The discovery sparked immediate speculation. Some observers suggested this might indicate unusual physics at work, perhaps even artificial light sources or propulsion systems that preferentially emitted material toward the Sun. The pattern seemed counterintuitive. How could dust move toward the Sun when radiation pressure should push it away? Hubble's detailed imaging provided answers that were interesting, even if less exotic than artificial explanations. The forward glow resulted from asymmetric heating combined with the object's rotation. When sunlight strikes a comet nucleus, it does not heat the surface uniformly. The side facing the Sun receives maximum radiation, and reaches the highest temperatures. As the nucleus rotates, different surface regions experience varying levels of heating throughout each rotation cycle. If the nucleus contains volatile materials that sublimate readily when heated, gas jets can erupt from the warmer regions with substantial force. These jets carry dust particles along with the gas. Depending on the angle at which jets emerge from the surface and the rotation axis orientation, dust can be ejected in nearly any direction, including toward the sun. The key lies in understanding that dust does not respond instantly to radiation pressure. When first ejected, dust particles travel in essentially straight lines, determined by the velocity imparted by the gas jets. Only after moving some distance from the nucleus does radiation pressure begin significantly affecting their trajectories. This creates a region near the nucleus where dust can exist in all directions, including sunward, before radiation pressure eventually sweeps it into the traditional antisolar tail. The forward glow therefore represented a sunward-directed dust plume, driven by asymmetric outgassing from rotating nucleus. Jets erupting from the surface facing toward or partially toward the sun created a fountain effect, with dust initially moving sunward before being gradually deflected by radiation pressure. The result was a brightness enhancement that appeared to defy the usual rules, but actually demonstrated well-understood comet physics operating under specific geometric conditions. Hubble's imaging also allowed astronomers to estimate the nucleus size. Measuring comet nuclei is notoriously difficult because the bright coma typically overwhelms the faint light reflected from the solid nucleus itself. By carefully analyzing the central brightness peak and accounting for coma contributions, researchers estimated the nucleus diameter at somewhere between 0.44 and 5.6 kilometers. This uncertainty range reflected the challenges of separating nucleus light from surrounding coma emissions. The size estimate placed 3 Ardsley Atlas within reasonable expectations for interstellar objects. Not as large as early speculation suggested, but substantial enough to survive millions of years traveling through interstellar space without being completely destroyed by cosmic ray bombardment and micrometeorite impacts. The forward glow, while initially mysterious, ultimately reinforced the natural comet interpretation, rather than suggesting artificial origins. The phenomenon demonstrated that 3I Atlas behaved according to established comet physics, albeit with specific geometric and compositional properties that created unusual but explainable brightness patterns. Ground-based observatories continued monitoring how the brightness distribution evolved as the object approached the sun, and its rotation carried different surface regions into sunlight. The forward glow's intensity and structure would change if new jets activated or existing jets shut down as heating patterns evolved. These variations would provide information about surface composition and how volatile materials were distributed across the nucleus. The mystery had been solved not through exotic physics, but through careful application of known principles. 3I Atlas was revealing itself as a natural comet, unusual in composition and behavior perhaps, but operating according to physics that governed comets throughout the solar system and presumably throughout the galaxy. Abraham Loeb is not a fringe scientist. As the Frank B. Baird Jr. Professor of Science at Harvard University and former chair of the astronomy department, he has published hundreds of peer-reviewed papers on topics ranging from black holes to the early universe. his credentials are impeccable. His ideas about 3I Atlas, however, have proven deeply controversial. Loeb examined the trajectory data and calculated something he found troubling. The object's orbital plane aligned remarkably closely with the ecliptic, the flat plane in which Earth and most planets orbit the Sun. While 3I Atlas travelled in retrograde motion, moving opposite to the planet's orbital direction, its path tilted only about 5 degrees off the ecliptic plane. Most interstellar objects should arrive from random directions, reflecting the chaotic dynamics of how objects get ejected from planetary systems and scatter through galactic space. The galaxy has no preferred plane. Stars and their planetary systems orbit the galactic center at various inclinations. An object ejected from one system and wandering for millions of years should approach our solar system from any direction with roughly equal probability. Yet 3I Atlas arrived nearly aligned with our planetary plane. Loeb calculated the probability of such an alignment occurring by pure chance. Using his assumptions about how interstellar objects should be distributed in velocity and direction, he arrived at approximately 0.005%. That translates to about 1 in 20,000. Not impossible, but unlikely enough to warrant attention. He found the sequence of planetary encounters even more intriguing. The trajectory carried 3I Atlas past Mars in early October, past Venus at greater distance, within remote range of Earth, and finally close to Jupiter in mid-March. This cosmic itinerary visited the 4 largest or most scientifically interesting bodies in the inner and middle solar system in sequence. To Loeb, this pattern suggested something other than random chance. If an advanced civilization wanted to survey our solar system, what trajectory would they choose? Perhaps one that enabled close observation of multiple planets while minimizing the risk of collision or detection. The actual path of 3I Atlas, Loeb argued, resembled what mission planners might design for a reconnaissance probe. He also noted the timing of perihelion passage. The closest approach to the Sun occurred when 3I Atlas was positioned behind our star from Earth's perspective. This geometry created an observational blackout lasting several weeks during the most active phase of the object's passage. If concealment was a priority, Loeb suggested, scheduling perihelion behind the Sun would minimize observation opportunities from Earth's largest concentration of telescopes. Loeb drew on concepts from science, fiction, particularly Liu Cixin's Remembrance of Earth's Past trilogy, which introduced the dark forest hypothesis. This idea proposes that the universe might be filled with civilizations that remain hidden because revealing one's existence could invite destruction from more powerful species. If survival depends on stealth, then any interstellar probe would be designed to observe while remaining undetected or disguised as natural phenomena. In this framework, 3I Atlas could represent a sophisticated reconnaissance mission. The object would arrive disguised as a comet, complete with outgassing and dust production, to mimic natural behavior. It would follow a trajectory that enabled observation of multiple planets. Its perihelion behind the Sun would provide operational security during critical maneuvers. Any technological signatures would be subtle enough to remain below detection thresholds of current instruments. Loeb acknowledged that his interpretation required extraordinary evidence, which current observations had not provided. No course corrections had been detected. No artificial emissions appeared in the spectra. The object behaved remarkably like a natural comet in every measurable parameter. But he argued that absence of evidence was not evidence of absence, particularly if advanced technology was designed specifically to avoid detection. His calculations about trajectory probability became focal points for criticism. Other astronomers noted that calculating odds after observing a specific event suffers from selection bias. Any particular trajectory will appear improbable when analyzed after the fact. The question is not whether this specific path seems unlikely, but whether it represents a meaningful deviation from expected interstellar object behavior, given our extremely limited sample size of 3 confirmed visitors. Critics also pointed out that Loeb's probability estimates depended heavily on assumptions about interstellar object velocity, distributions, and directional preferences, parameters about which we have almost no empirical data. Different reasonable assumptions could produce very different probability calculations. Yet Loeb's hypothesis, however controversial, had an important effect. It motivated more detailed observation campaigns and forced the scientific community to articulate precisely what evidence would constitute proof of artificial origin. Spectroscopy reveals chemical composition by analyzing how atoms and molecules absorb or emit light at specific wavelengths. Each element produces a unique fingerprint, a pattern of spectral lines that identifies its presence as reliably as human fingerprints identify individuals. When the Very Large Telescope in Chile pointed its ultraviolet and visual Echelle spectrograph toward 3I Atlas, astronomers detected something unusual in the light passing through the object's coma. The spectra showed emission lines characteristic of neutral nickel atoms. Nickel, element number 28 on the periodic table, appears in the spectra of some solar system comets, though not commonly. Finding it around 3I Atlas was interesting, but not immediately alarming. What caught attention was what the spectra did not show: iron emission lines, which astronomers expected to accompany nickel, were either completely absent or too faint to detect above background noise. This pattern struck some researchers as odd. Nickel and iron are chemically similar elements that often occur together in cosmic environments. They form in the same nuclear processes inside dying stars. When a massive star explodes as a supernova, it disperses both elements into surrounding space, where they eventually incorporate into new stellar systems and planetary bodies. In most natural contexts, anywhere you find nickel, you expect to find iron in comparable or greater abundance. The Earth's core consists primarily of iron with some nickel mixed in, a ratio of roughly 15 parts iron to 1 part nickel. Meteorites show similar patterns. The metallic compositions throughout the solar system reflect the ratios in which these elements formed during stellar nucleosynthesis and survived the processes that built planets and smaller bodies. Loeb and other researchers who favor exotic interpretations suggested the nickel without iron pattern might indicate processed metals. Industrial refinement could potentially separate nickel from iron, creating alloys with specific ratios designed for particular purposes. If 3I Atlas contained manufactured materials rather than natural cosmic dust, the spectroscopic signature might reflect engineering choices rather than natural abundances. However, mainstream astronomers quickly pointed out multiple problems with this interpretation. First, the absence of detectable iron lines does not prove zero iron abundance. Spectroscopy has limitations. Different elements emit their characteristic light, only under specific conditions of temperature, density, and radiation field strength. The physical conditions in 3 I-Atlas's coma might favor nickel emission while suppressing iron emission below detection thresholds. Atomic physics explains why. Nickel atoms can be excited to produce emission lines under conditions that leave iron atoms in their ground state, unable to emit detectable light. The energy required to excite an atom depends on its electronic structure. Nickel and iron, despite being neighbors on the periodic table, have different excitation requirements. If the coma temperature, density, or radiation environment happened to fall in a range that efficiently excited nickel but not iron, the spectra would show exactly what observers detected. Second, nickel has appeared in previous comet spectra without triggering speculation about industrial processing. Comet Hyakutake in 1996 showed nickel emission. So did Comet Hale-Bopp in 1997. Solar system comets occasionally display nickel lines when conditions are right. The detection around 3 I-Atlas was unusual but not unprecedented. Third, even if the nickel to iron ratio differed from typical cosmic abundances, natural processes could produce such variations. Chemical fractionation during comet formation can concentrate certain elements relative to others. Thermal processing, whether in the original protoplanetary disk or during the interstellar journey, could selectively remove or alter different elements. Cosmic ray bombardment over millions of years might affect iron and nickel differently based on their nuclear properties. The analytical challenges of extracting accurate abundance ratios from spectroscopic data should not be underestimated. Comets are complex, dynamic environments. Multiple emission regions exist at different temperatures and densities. Dust clouds obscure parts of the coma. Contamination from solar light reflecting off dust particles complicates the spectra. Determining precise elemental abundances from these messy observations requires sophisticated modeling and carries substantial uncertainties. What appeared to be missing iron might simply reflect limitations of current observations rather than genuine absence. Higher spectral resolution, different observation timing, or observations at different wavelengths might reveal iron lines that initial surveys missed. The question remained open, requiring more data before drawing conclusions about whether the nickel without iron pattern represented anything anomalous. The detection illustrated how even straightforward observations can generate multiple interpretations depending on what assumptions one brings to the analysis. The same spectroscopic data supported both natural and exotic explanations, neither definitively proven nor ruled out. The concept originated in science fiction, but has found serious consideration among scientists who study how civilizations might behave on galactic scales. Chinese author Liu Tixin introduced the dark forest hypothesis in his Remembrance of Earth's Past trilogy, proposing a chilling solution to the Fermi paradox, the question of why we have not detected signs of alien civilizations, despite the vast number of potentially habitable worlds. The logic proceeds from several assumptions. First, survival represents the primary goal of any civilization. Second, civilizations cannot know whether other civilizations they encounter will be friendly or hostile. Third, technological capabilities grow over time, potentially enabling a weaker civilization today to become a threat tomorrow. Fourth, the distances between stars and the speed of light limit make communication and verification of intentions extremely difficult and time-consuming. Given these constraints, the hypothesis suggests that revealing one's existence becomes extraordinarily dangerous. A civilization cannot know if contact will bring trade and cooperation or swift destruction from a more advanced neighbor. Because verification of another civilization's intentions might take centuries or millennia due to light-speed communication delays, the safest strategy is to remain hidden or to eliminate any discovered civilizations before they can pose a threat. The galaxy becomes a dark forest where every civilization hunts quietly, maintaining absolute stealth, knowing that making noise might attract predators. Any civilization that broadcasts its existence loudly through radio signals or other detectable emissions risks destruction. Survival depends on staying hidden and observing carefully. Loeb applied this framework to 3. I, Atlas. If advanced civilizations practice extreme caution when exploring other stellar systems, any reconnaissance probe would be designed to avoid detection. The ideal approach would involve disguising technological systems as natural phenomena. A probe that looked and behaved exactly like a comet would attract scientific interest, but not defensive responses from primitive civilizations that might perceive obvious artificial objects as threats. The timing of perihelion passage fit this interpretation. Positioning closest approach behind the Sun, from Earth's perspective, would minimize observation opportunities during the most critical phase of the mission. While space-based observatories at different positions might maintain sight lines, the vast majority of Earth's telescopes would be blind during perihelion, when the object might need to perform course corrections, deploy sensors, or conduct activities that could reveal its true nature. Loeb noted that the sequential planetary encounters would provide optimal reconnaissance coverage. A probe passing Mars could survey humanity's robotic presence on that world. The Earth flyby, though relatively distant, would enable observation of our planet's electromagnetic emissions, atmospheric composition, and potential biomarkers. The Jupiter approach would sample the outer solar system and possibly utilize gravitational assist for trajectory refinement. If 3 I-Atlas represented such a probe, its designers would have anticipated that primitive civilizations like humanity might detect and observe it. The disguise would need to be perfect, mimicking natural comet behavior in every measurable parameter. Outgassing rates would follow patterns consistent with solar heating. Chemical composition would resemble natural ices. Rotation and brightness variations would match expectations for an irregular nucleus tumbling through space. Advanced technology might enable such perfect mimicry. Programmable matter could adapt its properties to match environmental conditions. Artificial volatiles could sublimate on schedule to produce convincing comet activity. Sensors and communication systems could operate below detection thresholds of current instruments. The probe would become effectively indistinguishable from a natural object using any observational techniques available to 21st century astronomy. Critics challenged this reasoning on multiple grounds. If concealment was the priority, why approach so close to Mars and Jupiter, where observation would be easiest? Why not remain in the outer solar system, where detection probability would be minimal? Why follow a trajectory that passes through the plane of maximum spacecraft and telescope density? The dark forest hypothesis also requires that making noise is universally dangerous, which remains unproven. Perhaps most civilizations are peaceful. Perhaps the galaxy operates under different principles than the hypothesis assumes. Perhaps technological civilizations are so rare that encounters remain extremely unlikely, even over millions of years. Loeb acknowledged these objections, but maintained that the dark forest framework provided a useful lens for evaluating observations. If we assume advanced civilizations exist and practice stealth, what would their reconnaissance probes look like? They would look exactly like natural objects, behaving according to natural physics while quietly gathering information. 3. I-Atlas matched this profile perfectly, which proved nothing but justified careful scrutiny. The response from mainstream astronomy was swift and emphatic. NASA's official classification described 3 Chagral Atlas unambiguously as an active comet, period, with no caveats or suggestions that exotic explanations merited consideration. The European Space Agency echoed this assessment. Official statements from space agencies worldwide treated the artificial origin hypothesis as speculation disconnected from observational evidence. Leading comet researchers expressed frustration with what they perceived as premature sensationalism. Darryl Seligman at the University of Chicago emphasized the importance of exhausting natural explanations before invoking extraordinary alternatives. The history of astronomy, he noted, contains numerous examples of phenomena that initially seemed impossible to explain through known physics, but eventually yielded to patient investigation and improved understanding. Robert Lawler from the Planetary Science Institute pointed out that unusual chemistry does not automatically imply artificial origin. The universe is vast and diverse. Planetary systems form under widely varying conditions. Expecting every interstellar visitor to resemble objects from our own solar system reflects provincialism rather than scientific reasoning. 3. I-Atlas might simply represent comet chemistry, common in other stellar environments, but rare or absent in our cosmic neighborhood. Marco Micheli from the European Space Agency stressed the need for reproducible observations before drawing revolutionary conclusions. Extraordinary claims require extraordinary evidence, a principle often attributed to Carl Sagan. Single anomalous measurements or ambiguous signatures prove insufficient for conclusions that would overturn our understanding of humanity's place in the universe. The scientific community pointed to instructive historical examples. When pulsars were discovered in 1967, their regular radio pulses seemed so artificial that researchers briefly considered extraterrestrial beacon hypotheses. The signals were even nicknamed LGM for Little Green Men during initial analysis. Patient investigation eventually revealed rotating neutron stars as the natural mechanism producing these seemingly impossible periodic signals. Fast radio bursts discovered in 2001 initially appeared so energetic and brief that some researchers struggled to imagine natural processes capable of generating them. Speculation about artificial origins circulated in scientific discussions. Years of observations eventually revealed populations of these bursts with properties consistent with natural astrophysical phenomena, likely involving magnetars or other extreme cosmic environments. Tabby's star, officially designated KIC 8462852, exhibited bizarre dimming patterns discovered in 2015 that defied explanation through known mechanisms. The irregular, deep brightness drops sparked speculation about alien megastructures. Perhaps Dyson swarms constructed by advanced civilizations to harvest stellar energy. Subsequent observations suggested dust clouds, possibly from a disintegrating planet or comet swarm as more plausible explanations. The pattern repeats consistently throughout astronomical history. Anomalous observations generate exotic hypotheses. Media coverage amplifies speculation. Patient investigation reveals natural mechanisms previously unknown or poorly understood. The process advances scientific knowledge, but the premature excitement often damages public trust when revolutionary claims fail to materialize. Probability arguments like those Loeb presented face methodological criticism from statistics experts. Calculating odds after observing specific outcomes suffers from selection bias and what statisticians call the Texas sharpshooter fallacy, named for someone who shoots at a barn wall, then paints a target around the bullet holes. Any particular trajectory will appear improbable when analyzed in isolation, but the relevant question is whether it represents a meaningful deviation from expected behavior, given extremely limited data. With only 3 confirmed interstellar objects observed by humanity, drawing broad conclusions about typical versus atypical behavior invites error. What appears anomalous today might prove commonplace tomorrow as our census expands. The Vera Rubin Observatory, scheduled to begin operations soon, should detect hundreds of interstellar visitors annually. This dramatic increase in sample size will enable robust statistical analysis currently impossible. Regarding non-gravitational accelerations that might indicate artificial propulsion, current measurements show nothing anomalous beyond experimental uncertainties. Natural comets exhibit such accelerations routinely, as sublimating volatiles create rocket-like thrust effects. These forces follow predictable patterns related to solar heating, rotation periods, and volatile distribution. Detecting artificial thrust requires demonstrating systematic deviations from natural acceleration patterns, evidence that remains elusive for 3.I Atlas. The mainstream position emphasizes that scientific conservatism serves crucial protective functions. False positive declarations of extraterrestrial technology would damage credibility for decades, while potentially triggering inappropriate policy responses. The community learned painful lessons from premature announcements regarding Martian meteorite biosignatures in 1996, when initial claims of bacterial life in Martian rocks sparked worldwide excitement before careful analysis revealed more mundane explanations. Media amplification compounds these concerns. Speculative hypotheses presented as serious possibilities quickly transform into definitive claims through successive reporting cycles, creating unrealistic public expectations. Establishing clear criteria for what would constitute definitive evidence of artificial origin serves important purposes. It prevents goalpost shifting, where every natural explanation gets dismissed as inadequate without specifying what evidence would actually be convincing. It also helps focus observations on measurements that could distinguish between competing hypotheses. The most straightforward smoking gun would be persistent non-gravitational accelerations inconsistent with sublimation physics. Natural comets experience forces beyond gravity as outgassing acts like tiny rocket engines, pushing the nucleus in directions determined by where jets emerge and how the object rotates. These accelerations follow predictable patterns. They correlate with solar heating. They change systematically as the comet approaches and recedes from the sun. They produce forces proportional to the amount of material being vented. An artificial propulsion system would likely produce different signatures. Course corrections timed for operational reasons rather than thermal cycles, would appear as acceleration spikes, unrelated to solar distance. Thrust vectors pointing in directions inconsistent with observed jet locations would indicate hidden propulsion. Accelerations too large or too small for the observed outgassing rates would violate the physics of natural sublimation forces. Current astrometric precision allows detection of accelerations down to roughly 1/10 trillionth of an astronomical unit per day squared. This sensitivity approaches theoretical limits imposed by solar radiation, pressure, and measurement uncertainties. Any artificial system producing accelerations above this threshold while trying to mimic natural behavior would risk detection. The absence of anomalous accelerations in existing data either confirms natural origin or indicates that any hypothetical artificial systems operate below current detection thresholds. Artificial light curves represent another potential indicator. Natural objects tumbling through space produce brightness variations determined by their shape, rotation rate, and surface properties. An irregular, potato-shaped nucleus rotating on a stable axis creates periodic brightness changes as different cross-sections face observers. The pattern repeats predictably with each rotation. Artificial systems might exhibit different behavior. Brightness variations following programmed sequences, rather than rotational periods, would suggest active control. Sudden changes in rotation rate or axis orientation, without corresponding outgassing events that could explain the angular momentum transfer, would indicate attitude control systems. Optical signals modulated at frequencies impossible to produce through natural rotation would scream artificial origin to any astronomer. 3i Atlas shows brightness variations consistent with an irregularly shaped nucleus rotating with a period of several hours. The pattern appears natural, matching expectations for a tumbling comet nucleus. No anomalous brightness behavior has emerged from months of photometric monitoring. Structured repeating jet emissions could reveal deliberate control rather than passive thermal response. Natural comet jets activate when sunlight heats subsurface ice to sublimation temperature. They turn on and off as rotation carries different surface regions into sunlight. They grow stronger as solar heating intensifies closer to the sun. They may change over time as sublimation erodes surface layers and exposes fresh material. Artificial jets designed for attitude control or communication might operate on different schedules. Jets firing in sequences unrelated to solar illumination patterns would indicate active management. Emission timing correlated with planetary positions rather than the object's own rotation would suggest targeting specific observation opportunities. Jet strengths varying in ways inconsistent with thermal models would violate natural physics. Observations of 3i Atlas reveal jet activity consistent with solar heating-driven sublimation. The forward glow and anti-solar tail both match patterns expected from asymmetric heating of a rotating irregular body. No anomalous jet behavior has been detected. Narrowband radio or optical emissions would provide perhaps the clearest evidence. Natural processes generate broadband radiation across wide frequency ranges. Artificial transmitters concentrate power at specific frequencies chosen for communication efficiency. A signal at 21 centimeters wavelength, the famous hydrogen line, or any other frequency showing intelligent modulation would instantly confirm artificial origin. Radio telescopes have monitored 3i Atlas at various frequencies. No narrowband signals have been detected. The object remains radio quiet, except for the natural thermal emission expected from a body warmed by sunlight. Spectral features impossible to produce through known chemistry would demand artificial explanations. Emission or absorption lines from synthetic elements not found in nature, or molecular signatures of industrial compounds, never observed in cosmic environments, would indicate technological processing. Isotopic ratios, achievable only through nuclear engineering, would prove artificial manipulation. Current spectroscopy shows molecules and atoms expected in natural comets, albeit in unusual ratios. Nothing in the spectra defies natural chemistry. The carbon dioxide dominance, while uncommon, can be explained through formation in extremely cold environments without invoking industrial processing. The absence of these smoking guns does not eliminate artificial hypotheses entirely. Advanced technology might operate below current detection limits, but the burden of proof remains squarely on extraordinary claims, and that proof has not materialized despite intensive observation campaigns. The philosophical principle that extraordinary claims require extraordinary evidence serves as a cornerstone of scientific methodology. The maxim, popularized by Carl Sagan, though versions existed earlier, reflects a practical reality about how knowledge advances. Claims that align with established understanding require only modest evidence for acceptance. Claims that challenge fundamental frameworks demand proportionally stronger proof. This asymmetry makes sense when considering the accumulated weight of evidence supporting current scientific models. Thousands of observations across decades or centuries have established our understanding of how comets behave, how planetary systems form, how gravity operates. Any single new observation contradicting this vast evidential foundation should be treated with appropriate skepticism, unless the new data itself possesses exceptional quality and quantity. The history of science validates this conservative approach. Far more often than revolutionary discoveries overturning established paradigms, anomalous observations eventually fit into existing frameworks once better understood. The reluctance to embrace radical explanations has protected science from countless false paths, while still permitting genuine revolutions when evidence becomes overwhelming. Applied to 3, or I-Atlas, this principle establishes clear burdens of proof. The claim that it represents a natural comet with unusual chemistry requires only modest evidence. We know comets exist. We know they form in diverse environments. Finding one with exotic composition surprises nobody fundamentally. Slightly unusual does not equal impossible. The claim that it represents an alien spacecraft or probe requires vastly stronger evidence. We have never confirmed the existence of extraterrestrial technology. We have never detected artificial objects from other civilizations. The single instance would overturn our understanding of humanity's cosmic isolation while raising profound questions about galactic sociology, technological capabilities, and the prevalence of intelligence throughout the universe. The evidence threshold for accepting such a revolutionary claim must be correspondingly high. Ambiguous observations, unusual but explainable chemistry, and trajectory alignments that might be coincidental do not meet this threshold. Multiple independent lines of evidence, each individually compelling and collectively overwhelming, would be required before responsible scientists could conclude that 3 I-Atlas represents artificial technology. This does not mean extraordinary hypotheses lack value. Even incorrect theories can advance knowledge through several mechanisms. They motivate detailed observational campaigns that might otherwise not occur. They encourage development of new analytical techniques capable of detecting signatures previously unconsidered. They force articulation of exactly what evidence would constitute proof, clarifying the logical structure of different claims. Loeb's artificial origin hypothesis has generated precisely these benefits, despite lacking supporting evidence. His advocacy motivated enhanced observation coordination among multiple space agencies. It prompted radio telescope surveys searching for narrowband signals. It stimulated discussion about technosignatures and how we might recognize truly alien engineering. Even if ultimately wrong, the hypothesis has advanced our investigative capabilities. The scientific community's response also demonstrates healthy self-correction mechanisms. Extraordinary claims receive extraordinary scrutiny through peer review, independent verification attempts, and public debate among experts. This process, though sometimes contentious, ultimately strengthens knowledge by filtering speculation from substantiated discovery. False positives get caught. Weak arguments get exposed. Only claims surviving rigorous examination earn acceptance. The pushback against premature artificial origin claims protects multiple important interests. It maintains public trust in astronomical research by preventing cycles of hype and disappointment. It preserves the credibility needed for serious CT research that might someday detect genuine technosignatures. It ensures that when definitive evidence of extraterrestrial intelligence eventually emerges, if it does, the announcement will carry appropriate weight rather than being dismissed as another false alarm. Yet the tension between healthy skepticism and productive openness remains difficult to navigate. Being too conservative risks missing genuine discoveries or dismissing important anomalies. Being too credulous invites wasted effort on dead ends and damages scientific reputation. The balance requires constant adjustment based on evidence quality and claim plausibility. 3. iAtlas occupies interesting territory in this framework. Its anomalies are real. The carbon dioxide dominance, early activity, unusual polarimetry, and nickel signatures all represent genuine deviations from typical solar system comet behavior. These observations deserve serious investigation and may reveal important insights about comet diversity and interstellar object populations. But anomalies do not equal revolution. Unusual chemistry suggests formation in exotic environments, not necessarily artificial origin. Early activity indicates compositional or structural properties different from local comets, not technology. Each strange observation admits natural explanations consistent with known physics, even if those explanations require invoking environments or processes not previously well studied. The burden of extraordinary proof remains unmet. 3. iAtlas behaves like a comet in every fundamental respect. It outgasses. It develops a coma. It exhibits dust emission consistent with solar heating. It follows gravitational trajectories precisely. Its deviations from familiar patterns, while scientifically interesting, do not approach the threshold needed for accepting claims that would revolutionize our understanding of intelligence's cosmic distribution. Susan Falsner works at the Max Planck Institute for Radio Astronomy in Bonn, Germany, studying how planetary systems form and evolve. Her research focuses on the mechanisms that build planets from dust and gas in the disks surrounding young stars. In recent years, she has developed a hypothesis that could fundamentally change how we understand planet formation, a hypothesis that suddenly became relevant when 3I Atlas appeared. The standard model of giant planet formation faces a persistent problem that has troubled astronomers for decades. Building a gas giant like Jupiter requires first assembling a solid core massive enough to gravitationally capture gas from the surrounding protoplanetary disk. This core needs to reach roughly 10 Earth masses before the disk's gas disperses into space. The challenge is getting to that critical mass quickly enough. Conventional theory proposes that tiny dust grains collide and stick together through electrostatic forces, gradually building larger and larger aggregates. Millimeter-sized particles grow into centimeter-sized pebbles. Pebbles accumulate into meter-sized rocks. Rocks merge into kilometer-sized planetesimals. Planetesimals collide to form planetary embryos. Eventually, after millions of years of growth, a core reaches sufficient mass to begin capturing gas. But observations reveal a harsh deadline. Protoplanetary disks around young stars typically survive only a few million years before stellar winds and radiation disperse the gas into space. If core formation takes too long, the gas disappears before planets can capture it. This timeline pressure becomes especially acute for massive stars, which disperse their disks even faster through intense radiation and powerful stellar winds. Yet surveys show that more massive stars actually host giant planets more frequently than smaller stars. This correlation contradicts expectations from standard formation theory. If massive stars provide less time for core assembly, they should form fewer gas giants, not more. Something must be accelerating planet formation around these stars. Folsner proposed an elegant solution. What if young stellar systems do not need to build planetary cores from scratch? What if they can capture ready-made cores that already exist as interstellar objects drifting through space? A 5-kilometer object contains vastly more mass than the starting point of dust grain accumulation. Capturing such an object would bypass millions of years of slow growth, instantly providing a core capable of gravitationally attracting gas. The capture mechanism operates through gas drag. When an interstellar object encounters a young stellar system, it must pass through the protoplanetary disk if its trajectory happens to intersect that plane. The gas in the disk, though extremely thin by terrestrial standards, still creates friction on the passing object. This drag removes kinetic energy, slowing the object down. If enough energy is removed, the object's velocity drops below escape velocity, and it becomes gravitationally bound to the star. Once captured, the former interstellar wanderer becomes a planetary core. Its substantial mass gives it a strong gravitational field that can capture gas from the surrounding disk. It also attracts smaller solid particles through gravitational focusing, growing even larger. The accretion process proceeds rapidly because the core starts with such a size advantage over cores trying to build up from dust. Folsner's computer simulations revealed intriguing patterns. More massive stars appear more effective at capturing interstellar objects because their stronger gravity creates larger capture cross-sections. The probability that a passing object will be slowed sufficiently to bind increases with stellar mass. This prediction matches the observed correlation between stellar mass and giant planet frequency, providing circumstantial support for the capture hypothesis. The mechanism also explains rapid formation timescales. Captured cores could grow to Jupiter mass within hundreds of thousands of years, rather than millions, easily beating the deadline imposed by disk dispersal. This solves the timeline problem that has plagued conventional formation theory. For the hypothesis to work, interstellar space must contain sufficient wandering objects to supply young stellar systems with potential cores. Early estimates suggested interstellar objects might be relatively rare, making capture events improbable. But recent observations hint at much higher population densities than previously thought. If interstellar objects are common, capture becomes statistically inevitable over the millions of stars forming throughout the galaxy. 3I Atlas suddenly became relevant to this framework. Here was a confirmed interstellar object of appropriate size passing through our solar system. While too late to be captured by our ancient sun, it provided direct evidence that objects suitable for seeding planetary formation do indeed wander between stars. Its composition and structure offered insights into what capture candidates look like, information crucial for testing whether Falsner's hypothesis could operate in reality. Planet formation theory has wrestled with a fundamental timing puzzle for decades. The challenge involves reconciling how long it takes to build planets with how long the raw materials remain available. This mismatch between construction time and material availability has forced astronomers to develop increasingly creative solutions. Yet the problem persists especially for the largest planets. When a star forms from a collapsing cloud of gas and dust, not all the material falls directly onto the growing star. Conservation of angular momentum causes some material to settle into a rotating disk around the young star. This protoplanetary disk contains all the ingredients needed to build planets, dust grains, ice particles, and vast quantities of hydrogen and helium gas. But this construction site does not remain open indefinitely. Observations of young stellar clusters reveal that protoplanetary disks typically survive between 1 and 10 million years before dispersing. Several processes contribute to their destruction. The young star emits intense ultraviolet radiation that heats the disk's outer regions, causing gas to escape into space. Stellar winds, streams of charged particles flowing from the star's surface, sweep gas away. Nearby massive stars in the same stellar nursery contribute additional radiation that can strip away disk material. The clock starts ticking the moment the star begins shining, and within a few million years, the gas component of the disk largely disappears. This deadline creates no problem for rocky planets like Earth. These worlds form from solid materials, dust and ice, that remain even after gas disperses. They can take tens of millions of years to assemble through collisions and mergers. Earth itself likely required 30 to 50 million years to reach its current size, long after the solar system's gas disk had vanished. Gas giants face a much harsher constraint. Jupiter and Saturn consist mostly of hydrogen and helium captured from the protoplanetary disk. To accumulate these massive gaseous envelopes, they first needed solid cores, large enough to gravitationally bind gas against the tendency to disperse. Calculations suggest this critical core mass threshold sits around 10 Earth masses. Below that value, gravity proves too weak to hold gas efficiently. Above it, runaway gas accretion can occur, allowing rapid growth to Jupiter-scale masses. The race becomes clear. Planetary cores must grow from microscopic dust grains to 10 Earth masses before the disk's gas disappears. This growth must occur within the few million years that gas remains available. Miss that deadline, and you can build only rocky or icy planets, not gas giants. The traditional bottom-up growth process struggles to meet this deadline. Dust grains collide and stick together through electrostatic forces, gradually building larger aggregates. But as particles grow past roughly centimeter sizes, they encounter the drift barrier. These pebble-sized objects experience strong gas drag that causes them to spiral inward toward the star on timescales of hundreds to thousands of years. They fall into the star before growing large enough to resist drift through their own gravity. Recent developments in pebble accretion theory have helped address this barrier. Once a solid body reaches roughly 1/100th of Earth's mass, perhaps 100 kilometers in diameter, its gravity becomes strong enough to focus the trajectories of passing pebbles, sweeping them up much more efficiently than random collisions allow. This gravitational focusing accelerates growth substantially compared to earlier models. Yet even optimistic pebble accretion calculations require several million years to build cores to the critical 10 Earth mass threshold. The timeline remains uncomfortably tight, especially around more massive stars, where disk lifetimes tend to be shorter due to more intense radiation and winds. The theory predicts that massive stars should form fewer gas giants because their disks disperse before cores can grow sufficiently large. Observations show exactly the opposite pattern. Surveys reveal that more massive stars host giant planets more frequently than lower mass stars. This correlation between stellar mass and planet occurrence directly contradicts what standard formation timelines predict. Something must be accelerating core formation around massive stars, allowing them to build gas giants despite having less time available. Alternative theories like gravitational disk instability offer one possible solution. If protoplanetary disks become massive and cold enough, gravitational instabilities might cause portions of the disk to collapse directly into planet-sized objects, bypassing the slow dust to planetesimal growth entirely. But this mechanism requires specific disk conditions that may not exist commonly, particularly around the more massive stars, where giant planets appear most frequently. The timeline problem remains one of planetary science's most persistent challenges, demanding explanations for how nature builds gas giants faster than our models predict is possible. The process of capturing an interstellar object into a bound orbit requires removing kinetic energy from that object. Understanding how this works illuminates why Falsner's planetary seeding hypothesis offers such an elegant solution to the timeline problem, while also revealing what conditions must exist for capture to succeed. Consider an interstellar object approaching a young stellar system from galactic space. It carries velocity that reflects its motion through the galaxy, rather than any relationship to the target star. These velocities typically measure tens of kilometers per second relative to the stellar system. The object follows a hyperbolic trajectory that would normally carry it past the star and back into interstellar space, just as 3I Atlas will do in our solar system. For the object to become gravitationally bound, something must slow it down. The required velocity reduction depends on how close the object passes to the star and the star's mass. Passing closer requires less velocity change, because the gravitational potential well is deeper. More massive stars can capture objects more easily, because their stronger gravity creates larger effective capture zones. But gravity alone cannot capture the object. An object approaching on a hyperbolic trajectory will leave on a hyperbolic trajectory unless some non-gravitational force intervenes. This reflects conservation of energy. The object enters the stellar system with specific kinetic and potential energy. As it falls toward the star, potential energy converts to kinetic energy, increasing its speed. Then, as it moves away, kinetic energy converts back to potential energy. Without energy loss, the object exits with the same speed it entered, merely deflected to a different direction. Gas drag provides the necessary energy dissipation mechanism. Young stellar systems possess protoplanetary disks containing gas at densities far higher than interstellar space. While still extremely thin by terrestrial standards, perhaps 1 billion particles per cubic centimeter compared to Earth's atmosphere with 10 billion trillion particles per cubic centimeter. This gas is dense enough to create friction on passing objects. When the interstellar object's trajectory carries it through the disk, collisions with gas molecules transfer momentum from the object to the gas. Each collision removes a tiny amount of kinetic energy from the object while heating the surrounding gas slightly. Trillions of collisions occurring as the object traverses the disk can collectively remove enough energy to drop the object's velocity below escape velocity. The effectiveness of gas drag depends on several factors. Larger objects experience more drag because they present bigger cross-sections to the gas. Denser disks produce stronger drag. Objects passing through the disk's midplane, where gas density peaks, experience maximum drag. The object's velocity matters because faster objects spend less time in the disk and experience fewer collisions. Falsner's simulations explored these parameters systematically. She modeled interstellar objects of various sizes, approaching stellar systems of different masses, with protoplanetary disks of varying properties. The calculations tracked whether each encounter resulted in capture or escape, building statistical predictions about capture rates. The results revealed that stellar mass plays a crucial role. More massive stars create deeper gravitational potential wells that require less velocity reduction for capture. They also tend to form from more massive molecular cloud cores, potentially creating more massive protoplanetary disks that produce stronger gas drag. Both effects favor capture around more massive stars. This prediction aligns beautifully with observations showing higher giant planet frequencies around more massive stars. If captured interstellar objects serve as planetary cores, the correlation makes perfect sense. More massive stars capture cores more efficiently, leading to more frequent gas giant formation. The size range of potential seed objects also matters. Objects smaller than roughly 100 meters experience insufficient gas drag to achieve capture in most encounters. The drag force scales with cross-sectional area, while gravitational binding energy scales with mass. Very small objects lack enough mass for the drag they experience to significantly alter their trajectories. Objects larger than perhaps 10 kilometers might be captured too rarely because such massive bodies are statistically uncommon in the interstellar population. The sweet spot appears to lie between several hundred meters and a few kilometers, exactly the size range that 3I Atlas occupies. Once captured, the former interstellar wanderer settles into an elliptical orbit around its new host star. Continued gas drag gradually circularizes this orbit over time, though the captured object retains significant eccentricity initially. Its orbital plane may differ substantially from the disk's plane depending on capture geometry, potentially explaining why some exoplanets orbit at high inclinations relative to their stellar equators. The captured object now begins its new role as a planetary core, ready to gravitationally attract both gas and solid materials from the surrounding disk and grow toward gas giant status. Astronomical surveys over the past 2 decades have revealed thousands of planets orbiting stars beyond our Sun. These exoplanet discoveries emerged primarily through 2 detection methods. The radial velocity technique measures how planets gravitationally tug their host stars, causing subtle velocity shifts detectable through spectroscopy. The transit method watches for periodic dimming as planets pass in front of their stars from our viewing angle. Both techniques work better for larger planets orbiting closer to their stars, creating observational biases that astronomers must account for when drawing conclusions. Despite these biases, clear patterns have emerged from the accumulated data. One of the most striking involves the relationship between stellar mass and giant planet occurrence. Stars more massive than our Sun host gas giant planets more frequently than smaller stars. This correlation appears robust across multiple surveys using different detection methods, suggesting it reflects genuine astrophysical reality rather than observational artifact. Quantifying this relationship requires careful statistical analysis. Surveys must account for detection efficiency, the probability of finding planets of different sizes and orbital periods around stars of different types. They must correct for the fact that some stellar types receive more observation time than others. They must distinguish genuine correlations from random fluctuations in datasets of finite size. After applying these corrections, the pattern persists. A star with twice the Sun's mass has roughly twice the probability of hosting a gas giant planet compared to a solar mass star. Stars with half the Sun's mass show correspondingly lower giant planet frequencies. The relationship is not perfectly linear and carries substantial scatter, but the overall trend proves statistically significant. This correlation puzzled astronomers because conventional planet formation theory predicted the opposite pattern. More massive stars form from more massive protoplanetary disks, which seems initially favorable for planet formation since more material is available. But more massive stars also emit more intense ultraviolet radiation and drive stronger stellar winds. These effects should disperse protoplanetary disks faster, providing less time for cores to grow to the critical mass needed for gas capture. The competing effects do not cancel out. Calculations suggested that the disk dispersal timescale decreases faster with stellar mass than the disk mass increases. More massive stars should therefore form fewer gas giants because their construction deadlines become too tight for conventional core accretion to complete before gas disappears. Yet observations showed exactly the opposite. More massive stars form more gas giants, not fewer. Something about the formation process must operate differently than standard models assume. Either cores grow faster around massive stars through some unidentified mechanism, or some alternative pathway to gas giant formation operates more efficiently in these systems. Falsner's capture and seeding hypothesis offers a natural explanation. If interstellar objects serve as ready-made planetary cores, then the correlation with stellar mass emerges directly from capture physics. More massive stars have stronger gravity that creates larger effective capture cross-sections. An interstellar object passing through the vicinity of a more massive star has higher probability of being slowed sufficiently by gas drag to become bound. The simulations quantified this effect. Folsner modelled populations of interstellar objects with various size and velocity distributions, encountering stellar systems of different masses. She calculated what fraction of encounters resulted in capture for each stellar mass. The results showed that capture probability increases roughly linearly with stellar mass across the range where most observed exoplanets orbit. This prediction matches the observed correlation between stellar mass and giant planet frequency. If captured objects account for a significant fraction of gas giant cores, the stellar mass dependence of capture efficiency would naturally produce higher planet occurrence rates around more massive stars. The hypothesis also explains why the correlation applies specifically to gas giants rather than rocky planets. Captured cores arrive already large enough to capture gas from the disk. They bypass the slow growth phase that limits conventional core accretion. This advantage matters only for gas giants that require rapid core formation to beat disk dispersal deadlines. Rocky planets can form slowly over tens of millions of years, long after gas disappears, so capture provides no particular advantage for their formation. Additional observational tests could strengthen or refute the seeding hypothesis. If captured cores retain chemical signatures from their formation environments in other stellar systems, giant planet atmospheres might show isotopic ratios or elemental abundances inconsistent with formation from local disk material. Future observations with next-generation instruments, like the James Webb Space Telescope, might detect such anomalies, providing direct evidence for or against the capture mechanism. For now, the correlation between stellar mass and planet frequency provides tantalizing circumstantial support for Folsner's radical idea. The 3 confirmed interstellar objects discovered so far exhibit wildly different characteristics, suggesting that wanderers between stars sample a remarkable diversity of formation environments and evolutionary histories. This chemical variety carries important implications for the planetary seeding hypothesis, because it determines what materials captured cores might contribute to growing planetary systems. 1I Oumuamua, discovered in October 2017, showed no detectable comet activity throughout months of observation. No coma formed around it. No tail developed despite close passage to the Sun. Spectroscopic observations revealed a reddish surface color consistent with organic compounds altered by radiation exposure, but detected no volatile emissions whatsoever. The object's most striking feature was its extreme elongation, with length perhaps 10 times greater than width based on brightness variations as it tumbled through space. This lack of volatiles suggested composition dominated by refractory materials, substances that remain solid at high temperatures. Perhaps Oumuamua consisted primarily of rock or metal with minimal ice content. Perhaps any volatiles it once contained had been stripped away during its ejection from its parent system, or lost during its journey through interstellar space. The object resembled an asteroid more than a comet, though its small non-gravitational acceleration hinted at some subtle outgassing, too faint for direct detection. 2I Borisov, discovered in August 2019, presented a completely different profile. This visitor exhibited vigorous comet activity with prominent coma and tail visible even in amateur telescopes. Spectroscopic analysis revealed water vapor, carbon monoxide, and other molecules in ratios closely matching typical solar system comets. The object's chemistry appeared unremarkable, suggesting formation in an environment similar to the outer regions of our own planetary system. Borisov demonstrated that not all interstellar visitors carry exotic compositions. Some wanderers apparently form under conditions nearly identical to our local comet-forming regions. This similarity makes sense, given that stellar systems throughout the galaxy likely follow similar physical processes during formation, with temperature and pressure gradients creating comparable chemical environments at equivalent distances from their parent stars. 3. I-Atlas now adds a third distinct chemical signature to this small sample. Its carbon dioxide dominance with an 8:1 ratio over water represents chemistry unlike either previous visitor and unlike typical solar system comets. This composition suggests formation in extraordinarily cold environments where carbon dioxide froze more efficiently than water ice, conditions perhaps existing in the outermost reaches of a massive protoplanetary disk or around a particularly cool parent star. The diversity across just 3 objects hints at the variety that must exist in the full interstellar population. If we have sampled 3 wanderers and found 3 different compositional types, the complete population likely spans an even wider range. Different stellar systems produce objects with varying ice mixtures, dust properties, organic content, and refractory abundances, depending on local conditions during formation. This diversity matters crucially for the seeding hypothesis. If captured interstellar objects serve as planetary cores, they import chemical signatures from their birth environments into their new host systems. A core formed around a metal-rich star might carry higher iron and nickel abundances than local disk material. A core from an extremely cold outer disk might contribute unusual ice mixtures. A core ejected from a carbon-rich stellar system could import organic chemistry unavailable in more oxygen-rich environments. The resulting planets would exhibit chemical fingerprints that exceed what purely local formation could produce. Their atmospheres might show isotopic ratios inconsistent with condensation from local disk gas. Their bulk compositions might include elements or compounds at abundances impossible to achieve through accretion of local materials alone. These anomalies would serve as smoking guns for the capture process. Current exoplanet observations reveal substantial chemical diversity among giant planets orbiting other stars. Some show atmospheres enriched in carbon relative to oxygen, the opposite of our Sun's composition. Others exhibit heavy element abundances far exceeding what models predict from local disk accretion. Many orbit at high inclinations relative to their stellar equators, suggesting formation or migration processes that differ from conventional scenarios. Conventional theory struggles to explain this full range of properties through purely local formation and evolution. Disk chemistry alone cannot easily produce the observed variety of atmospheric compositions. Standard migration mechanisms have difficulty accounting for the highly inclined orbits some planets exhibit. But if interstellar seeding contributes to planet formation, the diversity becomes natural. Captured cores arriving from various stellar environments would import their chemical heritage, mixing materials formed under different conditions throughout the galaxy. The resulting planets would display the observed chemical variety because they literally contain materials from multiple stellar systems blended together during formation. Evaluating whether 3I Atlas possesses characteristics suitable for effective planetary seeding requires examining its physical and chemical properties against theoretical predictions about what makes a good seed. The object offers our best opportunity yet to study potential seeding material in detail. While it remains accessible to observation, size proves crucial for capture efficiency. 3. I-Atlas measures between 0.4, 4 and 5.6 kilometers in diameter based on Hubble observations. This range, while uncertain, falls squarely within the optimal zone predicted by capture simulations. Objects much smaller lack sufficient mass for gas drag to significantly alter their trajectories during disk passage. Objects much larger exist too rarely in the interstellar population to explain observed planet frequencies. The intermediate size provides the right balance between capture probability and population abundance. Chemical composition matters equally. The carbon dioxide dominance indicates formation in extremely cold environments, suggesting the object contains substantial volatile reserves. These volatiles could facilitate rapid expansion during the early accretion phase if the object were captured by a young stellar system. Outgassing driven by stellar heating would create an extended atmosphere that increases the effective collision cross-section for intercepting disk materials. This enhanced cross-section would accelerate growth toward planetary mass scales. The early hydroxyl activity, detected when 3 I-Atlas was still beyond 3.5 astronomical units, demonstrates responsive sublimation physics. The object begins venting even under modest solar heating, indicating either high porosity that allows radiation to penetrate subsurface layers or volatile mixtures that sublimate readily at low temperatures. Either property would benefit a captured seed by enabling rapid volatile release once bound to a new host star. The mixed composition, containing both volatiles and refractory materials, provides advantages for core construction. Volatile components drive outgassing that aids particle capture. Refractory materials contribute to the solid mass needed for gravitational dominance. The combination offers versatility that purely rocky or purely icy objects would lack. The exotic dust properties revealed through polarimetry suggest grain populations with unusual size distributions or internal structures. These characteristics might reflect processing during the interstellar journey or formation in environments different from our solar system. If captured, such exotic dust might contribute distinctive signatures to the resulting planet's composition, potentially detectable through future atmospheric observations of exoplanets. The object's apparent origin from the galaxy's thick disk population, if confirmed, adds temporal depth to the seeding narrative. Thick disk stars formed during earlier galactic epochs, when metallicity and stellar density differed from present conditions. 3 I-Atlas might carry chemical memories spanning billions of years, materials forged around stars from previous generations of galactic evolution. However, this particular object will not test the seeding hypothesis directly through capture, because its hyperbolic trajectory will carry it away from our solar system after completing its current passage. Our Sun is too old, its protoplanetary disk long since dispersed. 3 I-Atlas serves instead as a reference sample, revealing what interstellar seeding materials look like and what properties they possess. The detailed characterization now underway establishes benchmarks for recognizing similar objects and understanding their role in planetary formation throughout the galaxy. Even without capture, 3 I-Atlas illuminates the cosmic seeding process. When people ask whether something might be alive inside 3 Eye Atlas, the question requires careful definition before meaningful discussion can proceed. The phrase "alive inside" encompasses three distinct concepts that differ fundamentally in their implications and plausibility. The first interpretation involves literal biology, microbial life forms existing within the object's interior in a state of dormancy. This scenario would require organisms capable of surviving conditions that seem incompatible with life as we know it. The interior temperature likely remains far below freezing throughout most of the journey. Cosmic radiation bombards the object continuously during millions of years in interstellar space. No liquid water exists to support metabolic activity. Any biological passengers would need to enter a cryptobiotic state, suspended animation, where all metabolic processes halt until environmental conditions improve. Earth provides examples of organisms with remarkable survival capabilities. Tardigrades can endure complete desiccation for decades, then resume normal activity when rehydrated. Certain bacteria survive radiation doses thousands of times higher than lethal levels for most life. Antarctic microbes remain viable in ice for hundreds of thousands of years. These extremophiles demonstrate that biology can withstand conditions once thought impossible for life. Yet, the combination of challenges during interstellar transit exceeds anything terrestrial organisms face. Radiation exposure accumulates over geological timescales. Temperature remains constant near absolute zero. No energy source exists to power even minimal metabolic maintenance. The physics appears marginally plausible if several meters of ice provide radiation shielding and organisms possess extraordinary resilience, but no observational evidence supports biological presence. The second interpretation ventures into biotechnology, materials, or systems that blur boundaries between living organisms and engineered devices. Synthetic biology research on Earth already produces substances with lifelike properties. Self-replicating molecules, self-repairing materials, and programmable matter that responds adaptively to environmental changes exhibit functional characteristics of life while remaining fundamentally artificial. Applied to 3I Atlas, this concept might explain seemingly deliberate outgassing patterns or adaptive responses to solar heating as products of sophisticated biotechnology rather than simple physics. The object could theoretically contain systems designed to optimize performance across varying conditions encountered during interstellar journeys. However, current observations show only behavior consistent with natural comet physics, with no indication of active management or programmed responses. The third interpretation embraces full artificiality, a spacecraft or probe, deliberately disguised as a natural comet. This scenario requires engineering capable of perfectly mimicking comet behavior while concealing technological signatures from astronomical observation. The camouflage would need to function across multiple wavelengths and remain convincing throughout months of intensive scrutiny from humanity's most powerful instruments. Each interpretation carries vastly different implications for our understanding of life's cosmic distribution and intelligence's prevalence throughout the galaxy. But all three currently lack supporting evidence. 3. Eye Atlas exhibits chemical and physical anomalies that intrigue scientists while remaining fully consistent with natural formation and evolution. The burden of extraordinary proof for biological or technological claims remains unmet despite extensive observation campaigns. Earth hosts organisms that survive conditions once considered absolutely incompatible with life, These extremophiles have expanded our understanding of biology's limits, while providing reference points for evaluating whether life could survive interstellar journeys lasting millions of years. Deinococcus radiodurans earned its nickname as the world's toughest bacterium through extraordinary radiation resistance. This microbe survives radiation doses exceeding 5,000 grays, roughly 1,000 times the lethal dose for humans. When radiation shatters its DNA into hundreds of fragments, the bacterium possesses repair mechanisms that reassemble its genome with remarkable fidelity within hours. This capability suggests that biological systems can potentially withstand cosmic ray bombardment if protected by sufficient shielding. Tardigrades, microscopic animals measuring less than 1 millimeter in length, demonstrate survival capabilities that seem almost impossible. They endure complete desiccation, losing up to 99% of their body water while entering a state called cryptobiosis. In this condition, metabolism drops to undetectable levels. They survive temperature extremes ranging from near absolute zero to above boiling. They withstand vacuum conditions and intense radiation. Experiments aboard the International Space Station confirmed they can survive direct space exposure for days. Antarctic ice cores contain bacteria that remained viable after hundreds of thousands of years frozen in isolation. When researchers extract and thaw these ancient microbes, some resume normal metabolic activity, as if their long dormancy never occurred. The mechanisms enabling such extended survival involve cellular repair systems, protective compounds that prevent ice crystal damage, and metabolic shutdown so complete that degradation processes effectively cease. These examples establish that Earth biology can survive individual extreme conditions: radiation, vacuum, desiccation, extreme cold, extended dormancy. The question for interstellar panspermia is whether organisms could survive all these challenges simultaneously over timescales measured in millions rather than thousands of years. Calculations suggest that several meters of ice or rock provide adequate radiation shielding to reduce cosmic ray exposure to levels terrestrial extremophiles tolerate. An object like 3I Atlas, with a radius measuring kilometers, could potentially harbor a protected interior zone where radiation doses remain biologically tolerable, even over million-year timescales. Temperature presents less difficulty because many organisms survive indefinitely at temperatures near absolute zero once fully frozen. Metabolic processes cease, but cellular structures remain stable. The challenge becomes preventing radiation damage from accumulating faster than repair mechanisms can fix when organisms occasionally warm enough for brief metabolic activity. The most severe constraint involves energy. Even dormant organisms require occasional metabolic activity to repair accumulated damage. Without an energy source, cellular machinery degrades through purely chemical processes that repair systems cannot reverse. Interstellar space provides no sunlight, no chemical gradients to exploit, no energy whatsoever beyond the object's residual heat from formation and occasional cosmic ray impacts. Perhaps organisms could exploit brief warming periods during stellar encounters, awakening temporarily to perform repairs before returning to deep dormancy. Perhaps unknown biochemistries exist that require no maintenance energy. Perhaps we underestimate life's resilience. The physics appears marginally plausible under carefully constrained conditions, but remains speculative without evidence. 3. I Atlas shows no biosignatures, no organic signatures inconsistent with abiotic chemistry, no isotopic ratios indicating biological processing. The alive inside hypothesis remains scientifically interesting, but observationally unsupported. The panspermia hypothesis proposes that life, or its chemical precursors, travel between worlds on natural spacecraft. The concept dates back over a century, but has evolved substantially as our understanding of both biology and astronomy has deepened. Modern versions distinguish carefully between different levels of biological complexity that might survive interstellar transport. The traditional scenario imagines rocks blasted from planetary surfaces by asteroid or comet impacts. These impact ejecta can reach escape velocity if the collision is energetic enough, carrying fragments of the parent world into space. Some calculations suggest that material from Mars has reached Earth through this mechanism, potentially delivering Martian microbes, if any existed when the rocks were ejected. However, impact ejection predominantly samples surface materials that have experienced significant processing. Atmosphere exposure, temperature cycling, and radiation bombardment at planetary surfaces create harsh conditions that may have already killed or damaged any biological content before ejection even occurs. The rocks carry materials from environments least likely to preserve fragile organic chemistry. Interstellar objects offer a more elegant alternative for panspermia. These wanderers likely sample deeper, more primitive materials that experienced minimal thermal processing. They condensed in the cold outer regions of protoplanetary disks, where organic chemistry can survive and complex molecules remain stable. Their interiors, protected by meters of ice and dust, provide natural radiation shielding far superior to surface rocks. The carbon dioxide dominance observed in 3I Atlas might serve multiple biological functions in a panspermia scenario. Carbon dioxide provides an excellent shielding material, remaining chemically stable across the temperature extremes of interstellar space. It could also serve as a carbon source for autotrophic organisms capable of fixing atmospheric carbon into organic compounds when conditions permit metabolic activity. During warm passages near stars, solar heating could create transient zones of liquid water within porous interiors. These brief environments might awaken dormant biology, enabling rapid reproduction and dispersal through outgassing before conditions freeze again. The organisms would need to survive repeated freeze-thaw cycles and long dormant periods between stellar encounters. The more conservative panspermia scenario involves delivery of prebiotic building blocks rather than fully functional organisms. Complex organic molecules, amino acids, nucleobases, lipids, could survive interstellar transit more readily than living cells. These chemical ingredients, delivered to young planets during heavy bombardment phases, might accelerate the emergence of life by providing ready-made molecular components rather than requiring everything to synthesize from scratch. 3. I-Atlas carries organic signatures through its cyanogen emissions, confirming complex carbon-nitrogen chemistry within its nucleus. Whether these organics represent abiotic synthesis or remnants of biology remains impossible to determine from current observations. The boundary between living organisms and sophisticated machines grows increasingly blurred as terrestrial technology advances. Synthetic biology now produces materials that exhibit lifelike behaviors, self-replication, adaptive response to environmental changes, self-repair when damaged, all while remaining fundamentally artificial constructs designed by engineers rather than evolved through natural selection. Programmable matter represents one research frontier where technology and biology converge. Scientists envision materials that reconfigure themselves according to programmed instructions, changing shape, density, or chemical properties to suit current needs. Such substances might grow, reproduce, and adapt while operating according to engineered algorithms rather than biological metabolism. Applied to interstellar exploration, biotechnology could enable remarkable versatility. A probe constructed from programmable materials might adapt its configuration for different mission phases, expanding solar collectors when near stars, compacting for radiation protection during deep space transit, deploying sensors when encountering planetary systems. The distinction between spacecraft and organism would become meaningless. If 3I Atlas contained such systems, the outgassing patterns might represent programmed responses rather than passive thermal physics. The forward glow could indicate deliberate material ejection timed for specific purposes. The chemical composition might reflect engineered volatiles designed to sublimate on schedule rather than natural ices responding to solar heating. However, creating biotechnology that mimics natural comet behavior perfectly while operating autonomously for millions of years presents extraordinary engineering challenges. The systems would need to anticipate unpredictable encounter conditions with diverse stellar environments, survive cosmic ray degradation of control mechanisms, and maintain functionality across geological timescales without any maintenance or external energy input beyond occasional stellar heating. Current observations reveal no signatures distinguishing 3I Atlas from natural processes. The outgassing correlates predictably with solar distance. The chemistry admits natural explanations. The trajectory follows pure gravitational mechanics with no anomalous accelerations. If biotechnology exists aboard this visitor, it operates with such perfect camouflage that detection remains impossible using current techniques. The biotechnology scenario remains intellectually fascinating, while observationally unsupported, interesting for exploring conceptual possibilities, but lacking evidence that would justify acceptance as serious explanation for 3I Atlas. Despite months of intensive observation using humanity's most powerful instruments, 3I Atlas has revealed no evidence supporting biological or technological interpretations. The object behaves consistently with natural comet physics across every measured parameter. No metabolic byproducts appear in the spectroscopic data. The detected molecules, carbon dioxide, water vapor, hydroxyl, cyanogen, all occur naturally through photodissociation and sublimation processes, requiring no biological explanation. No isotopic ratios suggest biological processing or fractionation by living systems. The outgassing patterns correlate predictably with solar distance and heating intensity. As 3I Atlas approaches the Sun, volatile production increases following thermal physics. No emission sequences disconnected from natural heating cycles have been observed. The jets and dust production match expectations for asymmetric sublimation from a rotating irregular nucleus. Astrometric measurements reveal no course corrections or trajectory modifications beyond what gravity and natural outgassing forces predict. The object follows its hyperbolic path precisely with no anomalous accelerations, suggesting artificial propulsion. Radio telescopes monitoring various frequencies detect no narrowband signals or modulated emissions. The object remains radio quiet, except for natural thermal radiation from a sun-warmed body. Chemical analyses show nothing inconsistent with natural cosmic chemistry. While the carbon dioxide dominance proves unusual compared to solar system comets, it admits straightforward explanation through formation in extremely cold environments without invoking industrial processing or biological activity. The observational evidence consistently points toward natural origin, despite the genuine anomalies that make 3I Atlas scientifically interesting. Exploring radical hypotheses serves valuable purposes even when observational evidence provides no support. The speculative scenarios surrounding 3I Atlas motivate scientific activities that advance knowledge regardless of whether the original ideas prove correct. Loeb's artificial origin hypothesis prompted enhanced coordination among space agencies for observation campaigns. Multiple telescopes aimed at 3I Atlas that might otherwise have prioritized different targets. Radio surveys searched for signals they would not have sought without the technology speculation. These additional observations expand our dataset, even if they ultimately confirm natural origin. The biological scenarios encouraged researchers to articulate exactly what biosignatures we could detect and what evidence would prove life exists within interstellar objects. Speculative frameworks also expand our imagination about what possibilities exist in the universe. Even incorrect hypotheses sharpen our investigative capabilities by requiring us to develop detection techniques for phenomena we have not yet encountered. The closest approach to Mars occurs on October 3rd, 2025, when 3I Atlas passes within approximately 30 million kilometers of the red planet. This distance equals roughly 1/5 the gap between Earth and the Sun, close enough for spacecraft orbiting Mars to capture detailed observations impossible from Earth-based telescopes. The European Space Agency confirmed that Mars Express and the ExoMars Trace gas orbiter will conduct coordinated observation campaigns using their imaging and spectroscopic instruments. These orbiters carry high-resolution cameras capable of resolving surface features on Mars measuring just meters across. When pointed at 3I Atlas, they should achieve far better spatial resolution than Earth-based observations allow. The reduced distance eliminates atmospheric distortion that plagues ground-based telescopes. Space-based observations from Mars orbit provide crystal-clear views unaffected by turbulence. Spectroscopic capabilities aboard the Mars orbiters could detect emission lines invisible from Earth due to atmospheric absorption. NASA's Mars Reconnaissance Orbiter might join the campaign if scheduling permits, adding its powerful high-rise camera to the observation assets. Perihelion arrives on October 29th, 2025, when 3I Atlas reaches its closest approach to the Sun at 1.36 astronomical units. Solar heating intensity peaks at this distance, driving volatile sublimation to maximum rates. Any materials hidden within the interior that require intense heating to vaporize should reveal themselves during this critical phase. Unfortunately, the geometry places 3I Atlas behind the Sun from Earth's perspective during this crucial period. The glare of our star block's direct observation from most ground-based and Earth-orbiting telescopes for several weeks surrounding closest approach. This observational blackout occurs precisely when the object should be most active. The timing struck some researchers as suspiciously convenient for a hypothetical probe seeking to minimize observation opportunities during sensitive operations. However, this interpretation requires assuming that alien engineers possess detailed knowledge of Earth's telescope distribution and observation capabilities. Several spacecraft positioned at different locations might maintain sightlines despite Earth's blocked view. The Solar and Heliospheric Observatory, stationed at the L1 Lagrange, point between Earth and Sun, could potentially observe depending on exact geometric alignment. The Parker Solar Probe, designed to study the Sun's corona from extremely close range, might capture unprecedented data on how the interstellar visitor responds to intense solar heating. Natural comets typically exhibit predictable changes following close solar encounters. Volatile production rates peak near perihelion, then decline as the object recedes. Surface layers may erode from intense heating, exposing fresh material underneath. The nucleus might fragment if thermal stresses exceed structural strength. Any deviations from these natural evolution patterns could indicate artificial control systems or biological responses. The post-perihelion observations resuming in early December will reveal whether 3I Atlas weathered its closest solar approach following natural physics or exhibited anomalies suggesting more exotic interpretations. The final major encounter occurs on March 16, 2026, when 3I Atlas approaches within 0.36 astronomical units of Jupiter, roughly 54 million kilometers. This represents an exceptionally close pass by the solar system's largest planet, offering unique opportunities for gravitational physics experiments. Jupiter's powerful gravitational field will bend the visitor's trajectory, imparting the final major perturbation, before 3I Atlas departs back into interstellar space. Precise tracking during this close approach could detect tiny deviations from pure gravitational predictions that might indicate artificial propulsion systems or unusual mass distributions within the nucleus. Theoretical proposals suggest NASA's Juno orbiter could modify its trajectory to observe 3I Atlas during the encounter. However, these proposals remain purely conceptual exercises rather than approved mission extensions. Fuel limitations, operational risks, and competing science priorities make trajectory modifications extremely unlikely without compelling evidence of extraordinary phenomena. The intense radiation environment near Jupiter adds another variable to the observation campaign. Jupiter's magnetosphere traps charged particles, creating radiation belts far more intense than anything Earth experiences. This harsh environment might trigger responses from hypothetical, biological, or technological components designed to operate in high radiation conditions. After Jupiter, 3I Atlas will coast outward through the outer solar system, gradually fading from view as distance increases and solar heating diminishes. The visitor will eventually cross the heliopause into true interstellar space, resuming the wandering that brought it to our cosmic neighborhood. 3 distinct outcomes emerge from the evidence, accumulated during months of unprecedented observation campaigns. Each carries profoundly different implications for humanity's understanding of planetary formation, life's cosmic distribution, and our place within the galaxy. The natural comet interpretation represents the most likely conclusion based on current data. 3I Atlas would join the catalogue of interstellar visitors as a chemically unusual but fundamentally natural object that expands our understanding of comet diversity. This outcome would refine population models of interstellar objects and enhance understanding of outer stellar system chemistry. The natural seed interpretation would revolutionize planetary formation theory while remaining entirely within established physical principles. If 3I Atlas represents typical material available for capture and seeding mechanisms, it would validate a new pathway for rapid gas giant formation. This outcome would transform our understanding of planetary systems from isolated formation events to collaborative creations involving material exchange across interstellar distances. The artificial interpretation would represent the most important discovery in human history if confirmed through definitive evidence. Verified extraterrestrial technology would instantly overturn assumptions about cosmic isolation, while raising profound questions about galactic sociology and the prevalence of intelligence. Planetary defense strategies would require fundamental revision. SETI research priorities would shift dramatically. The burden of proof for this extraordinary claim remains appropriately high and currently unmet. 3I Atlas has already succeeded in expanding human perspective, regardless of which interpretation ultimately proves correct. Whether this visitor proves to be a natural comet, planetary seed material, or something more exotic, it forces confrontation with fundamental questions about cosmic connectivity. The 3 confirmed interstellar visitors discovered so far represent a statistically meaningless sample. The Vera Rubin Observatory, beginning operations, soon should detect hundreds of interstellar objects annually, dramatically expanding our dataset and enabling robust statistical analysis currently impossible. 3I Atlas continues its journey toward appointments with Mars, the Sun, and Jupiter, carrying whatever secrets first formed around alien stars in distant epochs of galactic history. The observations will continue, the data will accumulate, the answers will emerge through patient investigation rather than premature speculation. The universe has demonstrated repeatedly throughout scientific history its capacity for presenting phenomena that exceed current understanding. This interstellar visitor serves as a reminder that cosmic mysteries await discovery throughout our galaxy's spiral arms and the dark spaces between stars where wanderers drift between destinies that might reshape civilizations and their understanding of reality itself.